Yeah. I prefer today's weather so much more than last week's, but not that any of y'all asked. Okay.
So, exam on Friday, y'all ready for that?
I didn't even realize there was an exam on Friday until like the weekend. So. Don't worry. You'll okay. You'll okay. All right, so what we're gonna go over today is this exam one practice question that I've made.
Finish your breakfast. The school bus will be here any minute.
Oh, maybe not school, but.
Okay. So I feel like this encompasses everything that we should know for the exam. I don't want to spend time on stuff that y'all don't need to spend time on. I'd rather spend time on stuff that, you know, we actually need help on. So for example, in the chat and in class, raise your hand if you feel like you need help on naming. And this is not a table that you fill out. Don't fill this table out because there's nothing to fill out on the table. This table is literally just to help you in case you were having trouble with I guess memorizing. I don't know. When I first saw this table, you kind of just aligned it in my brain, put it in the right folders that made me make sense of it. So maybe it'll help you too. Yeah, like number of oxygens, nitrogen always has a -1, sulfur -2, and phosphorus -3. Anyways. Are we good with naming? I'll skip all the naming part. Yes, no, no. I got a couple no's. What kind of name? Ionic or covalent? Okay. So because we had a large worksheet dedicated to naming, I'll save the naming for the end of today, just because that's already on our YouTube channel that you can go get this. It's honestly like similar practice, like similar types of problems that we had done, but it was a lot more.
Yeah, it is.
Yeah, but it was a lot more problems, and it's on our YouTube channel, so I'll save this till the end of today, okay? All right. You don't need to do number 2. I don't believe we're doing anymore. That was are you able to move it to the right direction? Yeah. We don't test y'all on hydrocarbons anymore, I'm pretty sure. I know last semester was the last, he didn't do it for whatever reason. So you can ignore number 2. All right, number 3. Undergoes a combustion reaction. It gives you the amount of starting material and it asks how much product will be produced. Do we all know how to solve this problem, or would we like to start with number 3?
Equation.
Oh.
Right up the equation.
Right up the equation. Okay, so yeah, we're gonna go over number 3 now. So first thing we should do is write out the chemical equation, right? So octane, CH8 reacts with what? What does octane react with in the combustion reaction?
How about you give it a go?
O2.
Oxygen, yeah. What's that noise? Okay, and then produces what?
Carbon dioxide and water.
Thank you. Yes, so CO2 plus H2O. All right, so first we need to balance this. So for combustion reactions, I always like to put a 2 in the first thing and then start balancing there. So then we realize we have 16 carbons here, so we need to put a 16 here. And we have 36 hydrogens here, so we need to have 36 here. So we need to multiply that by 18. And then we need to multiply this by 25 to even out our oxygens. So again, that's not that's a 2, that's a 2 and a 5. All right. So now we start with our number 1.2 kilograms of octane. Let's see, 8H18. Let's convert this to grams. What's our conversion for from kilograms to grams? How many grams are in a kilogram? 1,000.
1,000.
Yeah, thank you. Now, what's in our next section right here?
The mass of octane.
Yeah. So as he said, and as someone else said in class, we need to get the molar mass of octane. And the molar mass of octane is 114 grams per 1 mole. Make sure you put this in the right area on the denominator, so that your units cancel out. All right, and what's next?
Ratio,
What?
mole to mole ratio.
Yeah, multiple ratio from the balanced chemical equation. And we see that for every 2 moles of octane, it's asking specifically for carbon dioxide. So we're going to use 16 moles of CO2 is produced. Okay. Next thing, if it's asking me how many grams of carbon dioxide we need to. Okay. If it's asking how many grams of CO2 is being produced, we need to convert from moles of carbon dioxide to grams of carbon dioxide, and we use the molar mass, right? So 44 grams, 1 mole CO2. Into a calculator, you should get, after taking into consideration sig figs, you should get 3,700 grams of CO2. How was that problem? On a scale from 1 to 10, 10 being the hardest problem you've ever seen in your life. 5. Okay. 5. All right. Let's try another one. All right. So I'm going to give y'all just about 2 minutes to work on 4A. And if you get done with A within the 2 minutes, try 4B. And actually try, don't just wait for me to go over it, because you'll be able to see where I guess how much you know and how far you're able to get on these problems. So I'll give you 2 minutes. It's 5:10. We'll convene at 5:12. Okay, 5:13 because it just turned 5:11. On the clock. Did you ever see any assignments? Like total, or just the ones I haven't graded yet? Okay, so like 6. I graded like 11. Okay, a little bit more time. All right, 5:13. How far did y'all get, or were y'all able to get? Y'all don't need to raise your hand, just like blur it out. It's such an informal session we have here. Just, like, talk to us, have a conversation with me and Rich.
Like if you want to go up and write on Dylan's iPad, PR guess.
Exactly. So get out of my way. Anyone? Yeah. How far did you get?
Sorry.
Okay, so did you get through A with any problems, or was that A pretty easy?
Yeah, it was okay.
All right, so what did you do? What was the first thing you did for A, or in general?
Well, yeah, it gives us like 2.6 moles of
Yeah.
sodium. So then what it did was the mole-to-mole ratio.
Yeah.
And then because it's asking for molecules, right? So then you multiply by Avogadro's number,
So what is the mole-to-mole ratio?
3 to 1.
Okay, so you balance the chemical equation, right?
Yeah, yeah.
Okay. So you balance it by putting a 3 in these two areas. And then from here, you'll realize that for every 1 mole of sodium phosphate, 3 moles of silver nitrate are required. So make sure we put that in the right area. So 1 mole Na3PO4 and 3 moles of AgNO3. And you did that because you realized, hey, we're already given moles of sodium phosphate, and it's asking about a different thing. It's asking about silver nitrate, which are, to convert from one to the other, you have to use the molar ratio, right? Now what did you do?
And then because it's asking for molecules, then 1 molecule of silver nitrate would equal to Avogadro's number. Nitrate.
Yeah. So when I wrote this, I put molecules, but AgNO3 is not a molecule, it's a formula unit for what we call ionic compounds. So we wouldn't say molecule of AgNO3. I was a dumb person when I wrote this, apparently. And Avogadro's number is what? Everyone needs to have this memorized. I can't hear. Okay, perfect. 6.022 times 10 to the 23rd. All right, and that's all you did, you plugged it into the calculator, right? So when you do that, you should get 4.7 times 10 to the 24. Is that something you like what you got? This would be formula units of silver nitrate. All right. How do we feel about part A? Good, perfect. For part B, it's asking how many moles of sodium nitrate can be produced from 0.64 moles of sodium phosphate. So this one's actually a really easy one. We're going to start with our given, which was 0.64. A lot of students will just write the number. I always like to write the units, so that way it reminds me of what we have. So sodium phosphate. And to convert from sodium phosphate to our product of sodium nitrate, we need to use what? Yeah, so molar ratio found in the balanced chemical equation. So as seen here, 1 mole of sodium phosphate produces 3 moles of sodium nitrate. And that's what's going to go in our balanced chemical equation. So it's a 1 mole Na3PO4 produces 3 moles of NaN. To get 1.9 moles NaNO3 after sig fix. All right. How are we? Was number 4? Oh, we're not even done with number 4 yet. Again, so our letter C is saying 30 grams of silver nitrate are reacted with 21 grams of sodium phosphate, 19.2 grams of silver phosphate are produced. What is the percent yield of silver phosphate? All right. So do we all have a general idea of what to do? Yeah, perfect. What's our first step? What's that? Exactly. So whenever you're given information about 2 of the reactants, so in this case, our reactants are silver nitrate and sodium phosphate, and we're given the amount of each one that we have to be thinking about what is the limiting reactant. So I'm going to start with 30 grams of silver nitrate. Ag. Know from using a periodic table that the molar mass of silver nitrate is 169.8 grams for every 1 mole of Ag3. And we're trying to convert to our product of silver phosphate. So we need to use the mole ratio of silver nitrate to silver phosphate. It should be about 1 to 3, I believe. Or 3 to 1. Yeah. So for every 3 moles of silver nitrate, 1 mole of silver phosphate is produced. So 3 moles AgNO3 produces 1 mole Ag3PO4. And before I go any further and solve it out, I would just, before I calculate the amount of grams, I just usually convert to moles first. So that way, because you can use moles to find the limiting reactant as well. You don't have to convert all the way to grams. So in this case, you would get 0.05889 moles. That's Ag3PO4. And now we can just use this to find the mass, right? So we can find the theoretical yield. Yes or no? But we have to check to see if the other one was a limiting reactant, right? So the answer was no. 21 grams of sodium phosphate. All right, and we know the molar mass of sodium phosphate is 164 for every 1 mole. And the molar ratio for this is for 1 mole of sodium phosphate. What is it? 1 mole of silver phosphate is produced. You go 0.12 moles. Ag3, which one is our limiting reactant? Silver nitrate or sodium phosphate?
Silver nitrate.
Silver nitrate because it produced less of the product. Okay. So now we can just cross all this out. We're not going to use that. Next, we just need to find out what the theoretical yield is. So we use the molar mass of silver phosphate, which is going to be pretty large. I think it's around 418,604 grams for every 1 mole. And we'll find that out, we get 24.65 grams. So we know that's our theoretical yield. So percent yield, let me watch this up. Percent yield equal to our actual over our theoretical times 100. Our actual is given to us. So 19.2 grams was our actual yield, and that's from the problem again. Theoretical was 24.65 grams. Multiply this by 100 to get percent yield of about what is you?
78.
Yeah, 78%. So what I had on my key was 77.8 after sig figs. Which, you know, is 78%. Okay. How was that problem? I know Rich and I have done so many percent yield problems, so I hope that the people that consistently come to our sessions, I hope that that problem was fairly like a review for all the other percent yield problems that we've done. Okay, Rich, you want to come try one? All right, we'll give you about 2 minutes to start working on 5. I don't expect you to get through A and B, but at least hopefully you get through A within the 2 minutes. That way. Hold on. What door do you get? Except that she's your favorite. Hold on about that. She said this is to the there and check. She said in first chapter, they go over molecular overall theory. In this one. Six. Oh, you don't know this. This. That's exactly what Dory said. Every student tries to do. He tries to. You could have just brominated radical bromination and then did reaction. She said everyone should do the most. Okay, how many of y'all are done with A and B or just A?
So that's basically.
Walk around, y'all just tap me on the shoulder. Y'all help. Are you using the lightest color that you want? You hurt your eyes.
It's pretty.
See, a couple of y'all are still working, so I'll give y'all more time.
So about a minute and a half more. Ish.
What about on Zoom? How many of y'all? You can just put in the chat if you are still working, still need a little bit more time, or if you're done.
Scott Thomas already done.
Sky Thomas. Definitely. Right. A little bit more time, or it's good. Good. All right.
All right. What was y'all's first step in solving the problem? Balance the equation. So you did, which coefficient?
Two S plus three, split two, yields two S.
6 oxygens, 6 oxygens, 2 sulfurs, 2 sulfurs. Yep, that's good. What was your next step? Yeah, so 7.2 grams sulfur and 10 grams O2. So this is 32 grams, right, in 1 mole because of molar mass. Then same thing here, same exact molar mass, I do 32 grams in 1 mole. And then, right, you got to use your mole ratio. So we're going to convert it into our moles of the product. So that's 2 moles sulfur for every 2 moles of SO3. And we're going to do that again here. So we're going to do 2 moles, sorry, 3 moles. 3 moles O2 for every 2 moles SO3. Then if we solve that out using our fancy calculator device thing, maybe one needs to sign into the computer thing, calculator. So, problem. So if we do that, we get 0.225 moles of SO3 and 0.2083 moles of SO2. So with that being said, which of these is our limiting reagent?
It's the oxygen.
It is indeed the oxygen, because 0.2083 is less than 0.225. So this bad boy right here is our limiting reagent. So O2 equals. All right, now we have that all set up. What is the percent yield of the reaction? So percent yield, 12.42 grams of SO3. So 12.42 grams, is that our actual yield or theoretical?
Actual.
So this is our actual. Now we need to solve for our theoretical to find our percent yield. So 0.2083 moles of SO3. Then, right, how do we get to our theoretical yield from here?
the multimole ratio of oxygen and, oh, wait, no, you transfer to grams and then.
Yeah, you just convert it to grams. So for every 1 mole, that's gonna be, let's see, 16 times 3, that's 64. 16 times, no, that's not 64, that's 48. 48 plus 32, that is going to be a number that is equivalent to 80. So 80 grams for every 1 mole. Just to make sure, is that what y'all got as well, for molar mass around that area? So if we
Yeah.
solve that out, we will get 16.6-ish grams of SO3. Now, right, we can get our percent. So percent yield equals actual or theoretical times 100. So we have 12.42 divided by 16.6. And we'll get a percent yield of. What'd y'all get for the percent? I'm solving this out. 77.5. Just make sure. So if we do it, it's 12.42 divided by 16.6 times 100. So I actually got 74.8%. Probably just rounded wrong somewhere. We're done here, right? Sig figs and all that nonsense. You have the correct amount of sig figs. I'd say so, right? Because we have 3 sig figs right here. And then our final answer should have 3 sig figs, because that's the least amount. All right, y'all feeling good about this? Energized? You can do like a million of these problems on the test, eyes closed, pencil, or holding a pencil with your feet, you can do it.
No calculator. I'm just kidding. Just a calculator that is non-graphic, please.
Exactly. If you have a graphing calculator, we will take it from you. I think we did that last exam, so yeah. All right, any questions? Thoughts, concerns? Ready? Let's move on. How do y'all feel about empirical formula? Pretty good, you can do it in your sleep. All right, go ahead and try number 6. A compound is found to contain 63.52% iron, 36.48% sulfur. Find its empirical. I'll give y'all, it's a good number, say 2.75 minutes to solve this problem. After 90 minutes. Test right is 25 questions. So you should be taking approximately 3 minutes, 36 seconds per question. Doing some quick math.
Forget, when does a rearrangement occur in real graphs?
When you have. It's the same as any carbon cation.
So even for primaries?
Yeah. But the primary doesn't form, it like shifts right even before it forms.
So, for example. That's gonna go there, and that goes there.
Yep.
I got a synthesis tree. Be specific about the conditions, temperature, and pressure.
Insane. This thing's not gonna work.
Just like you said, James does. Temperature and conditions. Computation. So, who is solving the problems over here? That's how we're gonna be doing it on the test too. Good. I'll make sure y'all sit next to it. Oh, y'all, who's in Armand's class?
I think it's.
I was here. Okay. It says stellar rate my professor.
I just got it because my roommate's just, and I don't like to pass them.
Why not? Why not doctor?
But then it's terrible. But I have Armand for lab.
Yeah. It's funny, everyone that has Armand, once doesn't like it, then they go to JECM2 and they're like, I would be. So.
It's because he gives work.
Yeah.
So that's
College.
okay.
It's college. It's 100%. Software has.
Said there's some so this should be ready.
What temperature and pressure reading?
You don't do it.
Checks.
How's that? That's that.
Oh, that was.
It's not like.
Oh,
I think it's 100, like 500. 500. Are any of us like stumped? Okay. One person that wants to admit it, that's okay. Find the empirical formula. I know I might be your TA, but literally y'all don't need to be so formal. Just like talk to me and like tell me where y'all are. Thank you. See, like. Who else is lost? Anyone on Zoom able to get the problem? Raise your hand high with pride if you are lost. Did you get it?
I know.
Oh, wait, you? You got it? I'm gonna go check your answer really quick. Be awesome.
Give me a nice thing.
Wait a minute.
Are you doing the same one?
What did you get? Iron and sulfur?
I thought it was this one.
Oh, wait, no, you're right. I was on number 7 already. Okay. Go ahead, Rich.
Let's try to get some of y'all that are lost, let's try to find y'all again. Y'all at the lost and found elementary school. Got some good gems from there. All right, anyway, 63.52% iron, 36.48% silver. So what is always our first step whenever we're given percentages and asked to solve for an empirical formula? We went over it before. Was that sorry?
Say it loud with pride. What?
Balance.
There's actually something else. We gotta assume a particular thing about the sample. Yeah, always assume 100 gram sample, never given percentages. Because what you can do is just take these percentages and convert them to grams. So 63.52 grams of iron and 36.48 grams sulfur. So right, then what do? Yeah, so our molar mass of iron is gonna be 55.845 grams. And then this is for 1 mole. And for sulfur, it's gonna be 32 grams for 1 mole. If we solve that out in our calculator device, we'll get 1.137. And then this will be 1.1. So it's the ratio, right, is 1.14 to 1.37. This is sulfur, this is iron. Now what do? This is 1.1. What's that, sorry? Divide both by 1.137, because that's the smallest one. 1.137. 1.137. So if we do that, we get S as 1, and then we get FE as 1. Or S is approximately 1. It'll be like 1.0 or something. So our final empirical formula will be equal to FeS. Because there's 1 iron, 1 sulfur.
What is the name of this compound?
So it's like our 2 sulfur.
What is another name for this compound? That's correct.
So like,
Using your Latin names, did we learn those? Ferrous sulfide, there we go. Yeah, because whenever you have these types of, I guess, atoms, transition metals that only have 2 charges, like iron. Iron can either be a +2 or a +3. We denote the lower charge with the ending us, so ferrous, and then the higher charge with the ending ic, ferric. So if this was, I guess it would be Fe2S3. If that was the formula, it would be ferric sulfide. But this one would be ferrous sulfide, which is the same thing as iron 2 sulfide. Yeah.
So those of you that were lost, are y'all found now?
Unlost.
I thought we were on 7.
yeah, me too.
So, yeah.
Oh,
That is crazy. Crazy cool. So on number 6.
Good. But on 7, I'm lost.
all right. Number 7 though. Have y'all gotten a chance to work through that one? Since there were some misconceptions. All right, I'm gonna give y'all 3 minutes to solve this question. Since you should be spending about 3.5 minutes per question. On all of these tests. It's not too bad. Again, two parts on this. That's
Yeah, so you know, all the hydrogen. Or you know, yeah,
all the
yeah. So, and all the oxygen too, but that is.
Is that better? Yes.
These answers will be available after this Zoom class. We will post the key. How many more questions are in this?
Quite a bit.
We'll post the key. Let's make a deal on Thursday, just because I don't want. We'll make sure everyone like has a chance to solve it before looking at the key, because everyone, as soon as you get lost on a problem, everyone looks at the key. We don't want people looking at a key, because you can't do that on the test. So try to work these problems out for your homework. It's not for a grade. And the key will be posted hopefully Thursday after our session. Is that a deal? Deal. Deals all day.
Give it a 7 for that class.
Oh no. Confidence there? Praise for all of them. I'll make it up with 5. Are you?
I got so poor in the practices.
What?
I literally didn't do the chapter 14 and the chapter problems because I was so poor.
Yeah, Lauren, we'll be using the same questions on Thursday. We also have a session on Friday that will go over the rest if we don't finish on Thursday. If we do finish on Thursday, what we'll most likely do on Friday is, since this was our practice exam, we'll just go over, like, you can just bring questions in. Maybe, I think Dr. Armand goes over our practice test in class, so maybe we can go over that. If that works out. Anyone need more time, or are you just like lost? All right.
All right, to all the lost people, just get y'all found again. Okay, so after combustion with excess oxygen, a 12.501 grams of a petroleum compound produced 38.196 grams of carbon dioxide, 18.752 grams of water. A previous analysis determined that the compound does not contain oxygen. Who cares? Establish the empirical formula of the compound. All right. Anybody have any idea for a first step?
The carbon dioxide grams and water grams into moles.
Let's try that out. So convert 38.196 grams CO2 and 18.752 grams H2O. We do that, we get 44 grams for every 1 mole. And then we get 18 grams. for every one. All right, so we have our moles of carbon dioxide and our moles of water. What's next?
Ratio with CO2 and carbon, carbon is like CO2.
That's actually correct. So it's an empirical formula, right? So for empirical formula, we need to get the ratio of carbons and hydrogens to this molecule. Because there we have our moles, and then we can like divide by our smallest amount and do our usual empirical formula steps. So for every 1 mole of CO2, there is 1 mole carbon. How I got that right was if you look at CO2, there's 1 mole of it total. So for every 1 mole, there should be an equal amount of carbon because the coefficient on that carbon is 1. Similarly, 1 mole of H2O, there should be 2 moles of hydrogen. I got that is the coefficient for hydrogen is 2. So if we go ahead and solve this out, we should get 0.86809 moles carbon, and then 2.0812 moles hydrogen. Now, what do we do next? Divide by the smallest one. Which one is that in this case? Yeah, so in that case, we're gonna divide 0.86809. And then divide this by 0.86809. So CH, we have 1, 2, 2.4. 1 to 2.4. Right. Now, what's next? We gotta make our carbon and hydrogen's whole number, right? Because we can't have 0.4 of a mole. Or not, sorry, 0.4 of an element. So what number here will make these two ratios a whole number? You said 2, but if you do that, 2.4 times 2 is 4.8. So that's not a whole number. 5. Yeah, you would use the number 5. So you multiply this out by 5. And then what you get is 5 carbons. And then 2.4 times 5. We do that off to the side real quick. That would be 12. So H is 12. Therefore, our molecular formula is, sorry, not molecular formula, empirical formula is C5H12. Or as people in the organic chemistry community call it, pentate. So, those of you who are lost, are y'all found now? What part of this tripped y'all up?
At the beginning, like trying to get to like the moles of carbon and hydrogen.
So you just didn't know where
Yeah,
to
like
start.
Yeah, if it's asking for empirical formula, most empirical formula problems either give you the percentage of each element or the mass of each element. So we need to somehow get to the specific element, and the only way we could do that is by starting with the grams of each product and converting it to moles of the specific element, because that's the only way we can solve empirical formula problems, right? We either give them percents or masses of the elements. So that's the direction we want to go to for all these problems. In this case, they put you in a really weird starting position that not a lot of people are, I guess it trips up a lot of people. But hopefully you see that we still did a similar thing. We got to the moles of the specific element, right? Cool.
So for funsies, I'd say y'all's homework for Thursday is balance out this equation. And whoever shows up on Thursday with this thing balanced will get a prize. What from myself?
Okay.
Okay. So balance that out. First person to show me gets a prize. Okay, let's do this last problem. If the molecular formula has a molar mass of 216.15 grams, determine the molecular formula. This, of course, is in reference to the previous question. So our empirical formula, once again, is C5H12. I'm gonna give y'all a minute to do this. Should take no more than a minute. Back again, you need to get rid of people. Tall ranchers. About 30 seconds. You got that joke down. $15. Yeah, that's birthday. That's it.
I straight forward. It's gonna be 48. What are you gonna get, Kim, please don't say nothing, you gotta make up for Christmas.
It still works.
Or just like Christmas, huh?
Yeah, I'm also teaching her electrical, so. And time. Nobody seriously get that joke? How many of y'all have Armand in here, Dr. Armand? Yeah. All right. So what is our steps in solving the molecular formula equation? What's our formula? Find the AMU of the empirical formula. So if we do that, each carbon is like 12 and each hydrogen 1. So it's 12 times 5, 60 plus 12 at 72 grams per mole. What do we do next?
Like the molar mass of the molecular formula over that number.
You divide your molar mass of your molecular formula by that. So 216.15 divided by 72 is a number that is equivalent to approximately 3. Nobody cares if it's like 3.12, just run into 3. So, right, this is our ratio. Is this our final answer? What do you have to do with this number?
By the empirical formula.
Yeah, multiply by your empirical formula. So C5H12, we're gonna take everything times 3. 5 times 3 is 15, and 12 times 3 is 36. So our molecular formula is C15H36, and as we call it in the organic chemistry community, I don't even know. This is some long carbon chain.
You don't know that?
I mean, pentadecane or something. Probably. Yeah, but that's too much harder. You can't even call it that. Right. Any questions on this, comments, concerns?
So,
And with that, it is 6 o'clock in the PM. So y'all are free to PM me or Dylan if you have any questions, and y'all can get out of here. Peace.
have a good one. You want Thursday, at what time, Rich?
3 PM. Is this building room? I just sent an email to Dr. Armand today, so he probably should have it by sometime this week.
Okay.